So this is our third Generative AI Examples, this time for linear algebra. So recall from Module 2 when we were looking at exploration and preprocessing, we talked about converting into a numerical array and rescaling the feature columns. But then we said more sophisticated often uses matrix algebra. For example, every m by n array is a product in many different ways of an m by l matrix D with an l by n matrix F, where L is the smaller of m and n. In other words, any rectangular array A can be written as this product. We often call this D a data matrix, and we often call the F a feature matrix. This is known as a matrix factorization or a matrix decomposition. So let's let ChatGPT show us an example. In matrix algebra, please produce an example of a non-square matrix that is factored into the product of two other non-square matrices. And here's the result. It generates a 2 by 3 matrix A, 2, 4, 6 on the top, 1, 3, 5 on the bottom. And then it goes through until it gets a B cross C, and the final result, hey, wait a minute. That lower left coefficient is 0, but it needs to be a 1. ChatGPT, your last calculation is incorrect. It agrees with me. You see, large language models are not smart. They're models. They have to be properly handled in order to produce useful and correct results. So, ChatGPT tries again, and it fails. That didn't work. At least now it's doing matrix multiplication correctly. And still failing, but finally it gets the right answer. So, very often these matrix decompositions involve eigenvalues. Yeah, but what's an eigenvalue? Well, let's ask ChatGPT. What is an eigenvalue? Well, that's a terrible prompt. No context, no scale. So, in the matrix algebra of rectangular arrays, what is an eigenvalue? And here you see it produces essentially a definition of an eigenvalue, an associated eigenvector. It probably found this in Wikipedia. Probably the other prompt would have given us the same thing. But ChatGPT, can you show me an example of a 3 by 3 matrix? And sure enough, it generates this nice symmetric matrix A, shows us how to find the characteristic polynomial, and then we factor, and factoring gives us the eigenvalues, the zeros of that characteristic polynomial, 3, 6, and 3. Now we ask ChatGPT to find the associated eigenvectors. So how would I find the associated eigenvectors? Well, here it goes through and shows us how we're going to have to solve a system of equations, and it does so with lambda equals 3 and gets this v1 and v3, and for lambda equals 6 it gets this v2, and of course we'd probably need to ask it to verify its results, which it does. And now we can ask for the NumPy code. Okay, so why do we need eigenvalues? Well, an eigenvalue of a square matrix A is a number lambda in C such that AV equals lambda V for some non-zero V in Rn. Now we're going to look at some notation. Notice that I only have the diagonal entries here. And what I mean by that is all those blank spaces are where we have zeros. And the coefficients of the diagonal matrix are the eigenvalues of the diagonal matrix. Now that leads us to a thing called the spectral theorem. If A is a symmetric, A is equal to its transpose square matrix, then A is equal to Q times this diagonal matrix times QT, where QT times Q is the identity and QQT is the identity. In other words, we say that Q is an orthogonal matrix. So why? Well, what's this good for? Well, that's a fair question. Let's, for instance, look at A squared. Well, now we've got a formula for A squared, and A cubed, and A inverse if the inverse exists, and lots of other things that we can do with A simply by manipulating that diagonal matrix. Can we see an example? So this is the playground.openai.com. This is actually kind of what ChatGPT looks like under the hood, so to speak. Notice you can pick a specific model, and then you can actually set the context within which you're going to have this ChatGPT session. Our context, we want friendly examples from a linear algebra to 4 decimal places using standard matrix notation. And then we can ask our question. Here is my prompt. So I want to get the spectral theorem for this set of numbers interpreted as a 3x3 symmetric matrix. Now I'm actually going to use ChatGPT, better formatting, and also this playground isn't free. So here is my result. There's my matrix A. It says for the spectral theorem, we'll find the eigenvalues, find the eigenvectors, form the orthogonal matrix Q, and construct the diagonal matrix D. So there are the 3 eigenvalues and the corresponding eigenvectors. And we take those 3 eigenvectors and we put them as the columns of Q, and we put the eigenvalues on the diagonal of D, and therefore we get A equals QD Q transpose. And of course, we ask it to check and see that it actually got it right, and it did. So now we can generate some code for implementing the spectral theorem. So our ChatGPT prompts, we're going to define a matrix. We're going to go back to the 411411114 that it actually showed us earlier. And we want each coefficient to be interpreted as a real number. We're going to calculate the eigenvalues and eigenvectors of A, and then form the matrix Q of eigenvectors, and the D is the diagonal matrix of eigenvalues, such that we get the spectral theorem. And here is the result. So notice the Q and the D. And notice that I wanted these to be real numbers, and therefore it put a D type equals float in there, so I wouldn't run into any weird stuff. It was only working with integers. Now we can look at an application of the spectral theorem. A symmetric square matrix is said to be positive semi-definite if X transpose Sx is greater or equal to 0 for all X in Rm. So suppose we have a matrix A in Rm by n. Let's say non-square matrix, potentially. And look at its transpose. It's also going to be a rectangle, but the m rows of the original will now indicate that there are m columns in the transpose. We can multiply A times A transpose, and we get an m by m matrix. And we can multiply A transpose A and get an n by n matrix. And the nice thing is, you can show that A transpose A and AA transpose are both positive semi-definite matrices. And their non-zero eigenvalues are the same. So that means they both have a spectral theorem decomposition, where this U and this V are orthogonal matrices. And notice that the diagonal has the same non-zero values in both. Now these square roots of these eigenvalues are called the singular values of A itself. So here we have the singular values. The squares are the eigenvalues, non-zero eigenvalues of A transpose A and AA transpose, and we can actually prove that A itself is U times this matrix with just the singular values themselves on the diagonal and then B transpose. One very important thing to notice is we always write the singular values in non-increasing or decreasing order. So we always go from the largest to the smallest. This is known as the singular value decomposition. For any A that's a m by n matrix, doesn't have to be square, with column rank R, the singular values, these are lowercase sigma 1 to sigma r. These are positive numbers in decreasing order, not increasing. And we're going to have a capital sigma to the k for any positive integer k, actually denotes any matrix of this form. The first R entries on the diagonal are the sigmas to the k power, and everything else in the matrix is zeros. Then our theorem is that if A is in Rm by n, a possibly non-square matrix, then A is U sigma V transpose, and A transpose A is V sigma squared V transpose, where U and V are orthogonal matrices. In other words, our A looks like this, and our A transpose A looks like this. Whoa! Maybe you've never seen anything like that. Well, that's okay, because you have large language models like ChatGPT. Even at its most abstract, matrix algebra is actually logical to the point of being mechanical, something computers and large language models are good at. A large language model can literally, pun intended, carry on a conversation about even the most conceptual topics in matrix algebra. And the singular value decomposition is the fundamental theorem of matrix algebra. So I want to invite you to self-tutor on the singular value decomposition with an LLM, and even other topics. For instance, ask it about pseudo-inverses and projections. So I'll get you started. Now, just a note, we tend to prefer the Linear Algebra library in SciPy to the Linear Algebra library in NumPy. So here are my prompts. Let A be a NumPy array with columns 1, 2, 3, 4, and 5, 6, 7, 8 with real number coefficients. Use the Linear Algebra library in SciPy to calculate the singular value decomposition of A, where U and V transpose are the orthogonal matrices, and S denotes the singular values. Calculate A transpose, and then calculate U S squared U transpose, where S squared is the matrix square of S. And here is our result. However, ChatGPT actually gave me something that had an error. This is actually the AI assistant in Anaconda. So sure enough, we have that AA transpose is U S squared U transpose. That's what we expected. But I've actually fixed the code. So you can put these prompts in. It will give you code, but the code won't work. Can you work with the LLM to produce the code that you see here that actually works? Here's another. So do you know what's going on in this Python code? Well, see if you and ChatGPT or equivalent can figure it out. Have a conversation with it. If you're successful, you and your LLM should be able to determine what would need to change in order for the approximation to look exactly like the original, and by how much. The notebook with code and image is available on our website. And yes, you can simply give code to a large language model and say, explain this to me. Have a conversation about what it does and how you might want to modify it. So large language models in linear algebra. They're very helpful assistants in linear algebra. But you still have to know the linear algebra. And because large language models are best when they're assisting experts, they're actually not very good at instructing the uninformed. Hopefully you've seen that enough by now to believe that statement. So we're beginning in this course to have conversations with these large language models. And this is important because for large projects, you're going to have multi-scale requests across a range of different prompts. And you'll always need to remind yourself of the importance of scale.